Um, Hi. Okay, no, that's wrong. Okay, let me go through the hurdle of sharing my screen again. Okay, cool. Can you see my screen?
Yes.
Okay, great. First of all, thank you very much for the invitation. I know that I'm the last speaker, so I'll try to keep things interesting and short, so that we can conclude this amazing day of talks. So my name is Vassilis Charitopoulos. I'm an assistant professor from the Department of Chemical Engineering at UCL, and today I will present a collection of the work that we do within my group. This is a collaborative effort, so I would like to first of all acknowledge my co-authors from the group, Margarita Eftimiadou, Dr. Zouzou, Dr. Mohammed Hkemati, Professor Lazaros Papageorgiou, and also my collaborator from Cambridge Judge Business School, David Reiner. So I'm going to talk about hydrogen and its role for decarbonizing heat, focusing on the UK perspective. Um, so a little bit of the background on why we investigate this issue is because, first of all, heat accounts for almost a third of UK emissions, and 50% of that comes from residential heat. Uh, at the same time, the heating sector has been the most slowing move sector in terms of emission reductions, with only 17% reduction over a 30-year period span. And simultaneously, 70% of industrial UK energy demand comes from heat. At the same time, what is challenging here is the fact that a lot of the speakers spoke about how whole systems models, optimization models, requires tons of parameters. So regarding heat, we lack high quality data, and I will get into this in my next slides. Uh, when we talk about residential heat, also this is something that is consumer driven, while also when we speak about industrial heat, we have to deal with different heat qualities in terms of temperature grades. And finally, when we try to decarbonize heat, we need to be wary of health and social concerns because currently in the UK we have almost 6.1 million households under fuel poverty. So regarding the first point, before I delve into the modeling, we have to have some solid background on which we can draw nice results. The first issue was what is the real peak demand that we have in the UK? So we performed the study back in 2023, where we collaborate with local gas network distributors. And what we concluded was the fact that by using real world data, uh, even for the case of 2018, which in the UK we had a cold snap during February, our estimate using the data was 45% less than previously widely cited estimates in terms of the peak heat demand, and more aligned with some newly empirical studies from 2018. So first of all, you can see here the first hardship that we had in terms of data. Now, why heat is challenging in the UK? Heat is challenging in the UK because we have an incumbent gas fuel system, which is quite efficient. Before the war in Ukraine was quite cost effective as well. And 80% of that residential heat demand is served by gas boilers. And at the same time, in off-gas grid areas where we don't have a gas distribution network, we have a mix of electric heaters, not so much heat pumps, solid and oil burners, and these are more and the Scottish region and the Welsh region here. What is extra difficult as well is the seasonality. So heat is seasonal. It can be very high during the winter and not so high during the summer. Well, we're in the UK, so we get cold even in the summer. But regardless, this is what the heat demand curve looks like across different months and regions. And this brings a lot of issues regarding how you decarbonize this. So we've spoken about electrification. Electrification may not be a very straightforward option because of the seasonality and the additional stress that you put into your system. We have uncertainty regarding the demand, the timing, and the scale of heat. At the same time, we have a very slow technology uptake. So currently, we're looking at a moving average of less than 3,000 air source heat pump installations in the UK. We're also exposed to policy uncertainty. So the previous UK government want to proceed with a boiler ban that has been scrapped. So we have a lot of mixed signals towards the consumers for them to actually commit to specific technology and refurbish their homes. So the research viewpoint for the next few slides that I will try to take is first of all introduce our core of research, which is multi-scale optimization-based models. So we're talking about spatial explicit evolution-based models that cover different vectors. This particular presentation focuses on power and heat. We do not cover heavy transport, for instance. And we have a special interest about green computing. So tailored decomposition solution methods, uncertainty quantification modeling techniques, game theoretic methods for energy systems planning. So really trying to highlight the decentralized aspects of an energy systems planning problem, as well as I will show you at the very end a preliminary a prototype implementation of a user-friendly, accessible software for policymakers. So the first part, I will speak about integrated hydrogen and power decarbonization for heat. Here, the question that we're trying to address is what is going to be the role of hydrogen in the quest of decarbonizing simultaneously the heat and the power sector in Great Britain. So similar to previous speakers as well, we deal with a superstructure model where we have different set of technologies, different set of storage options, and interconnection between electricity and hydrogen, either for production of hydrogen or production of electricity, as well as the satisfaction of heating demand. And here, in terms of heating demand, we have different scenarios ranging from just residential and the commercial, but also the industrial use. And again, these all come from real past data, so we can capture really well the seasonality and granularity across the different regions. In terms of spatial resolution, our model covers the 13 local distribution zones in the UK according to the gas network operators, and we have 5 and 10 year time steps between 2030 and 2050, where we have a set of representative days and different configurations depending on the model that we want to explore. And at the very end, we have an hourly resolution because we really want to also take into account flexibility aspects of the system. In terms of mathematical modeling, this is a cost minimization problem covering both CapEx and OpEx of the different components, a set of constraints, and we want to get decisions about the investment of production, storage, and allocation of hydrogen and heat. So this is all formalized as a combinatorial mixed integer linear programming model. Now, the problem, as we will see later on with these kinds of models, because of their combinatorial nature, is that they're not so friendly for what-if analysis, because a single solve of a single solution of this model can take up to 2 days to run. So going into the results, the first case that we explored was simply the residential and commercial demand. So as you can see here, for the case of our model, we have a large set of continuous and discrete variables. We can solve this model in 2.5 hours. And what we observe here is that as we move towards 2050, the role of hydrogen within this aspect, we have a lot of investment in terms of steam methane reforming and thermal reforming for hydrogen production and water electrolysis after 2040, together with increased capacity of wind farms and solar farms in 2050. So we compute that we will need more than 100 gigawatt of hydrogen capacity to proceed with the decarbonization of heat for the residential and the commercial sector. Now, what this looks like, when we allow the model to either select air source heat pumps or hydrogen boilers, we see that we end up with a 28% decarbonization of heat through hydrogen. And we can actually get some results about the allocation of those hydrogen installations. And these are mostly in the northern regions of Great Britain. And for those of you who are familiar with this setup, it kind of makes sense because here is also where we have a lot of industrial activity. Now, as I said, in the first case, we investigated an exclusive or kind of relationship where we have either air source heat pumps installation, gas boilers up to 2030, and then hydrogen boilers. So this is our base case. We have a hydrogen gas flexible scenario where we have a hybrid hydrogen gas boiler setup, and we allow blending of hydrogen and gas in the system, and a final scenario where we have a hybrid hydrogen air source heat pump setup. And as you can see, when we consider increased flexibility, the total capacity installed for across the different technologies reduced significantly by more than 30%, and so does the total system cost. So relating to the technology adoption from the end use sector, you can see that this can have a massive effect on the capacity expansion planning of the future system. Relating to CO2, because of the deployment of biomass gasification technologies, we also have negative carbon emissions. So the case where we have a flexible hydrogen and gas configuration for heating homes, we still get some negative emissions, mostly coming from the power sector. But the most negative emissions that we get is for the case where we allow a hybrid installation of air source heat pumps and with a hydrogen component. Going into further details, this is what in the base case hydrogen allocation looks like. So we have almost a 50-50% split between hydrogen for heat and electricity. In the case that we allow air source heat pumps or hydrogen gas boilers, we see that most of the hydrogen is directed towards heat and less so towards electricity, because here we don't stress a lot our electricity system to capture, to satisfy the heat demand. And at the same time, when we allow flexible configuration between air source heat pumps and hydrogen, most of the hydrogen is gone towards heat to satisfy, again, the seasonality and the peak demands of the heating sector. A third case is where we added on top the component of industrial decarbonizations for heat. So we have one very optimistic scenario, which is basically that industrial heating can be fully electrified by 2050. And up to a certain point, to the degrees of 1000 Celsius, there are some technologies that can be ready for this by 2050. A second scenario is where we push hydrogen heat to be exclusively met by hydrogen. And then a scenario 3 where we have either satisfaction of heat demand from hydrogen or electricity by 2050. In all three scenarios, we can see that we drive a lot of negative emissions from the heat sector. What is very interesting is when we add on top of the component of the power decarbonization, the heat decarbonization, the spatial allocation of the generation technologies in Great Britain varies significantly. And we can see that renewable electricity generation is predominantly located to southern England, whereas full electrification of heat requires increased gasification-based hydrogen generation, as well as fuel cell for electricity generation. We also observed the trade-off between the levelized cost of electricity and the levelized cost of hydrogen across the different scenarios, where we can see here that, again, in the case that we have a flexible setup between gas and hydrogen, this is where we meet the lowest cost for hydrogen. I'm sorry, you must be hearing my dog, but yeah. And we can also see that adding the component of industrial decarbonization significantly reduces the levelized cost of hydrogen as well. Now I will move to the second part of the presentation, which is how we deal with uncertainty. So this is work that we published in Applied Energy earlier this year. So our main motivation was the fact that these kind of multi-scale models at their very core have some sort of temporal compression algorithm. The problem with that is that typically you have historic electricity demand data or gas demand data, and then you would pick a median profile, and based on that, you would run your model. And the idea that we had was that, okay, what happens when we want to actually quantify the uncertainty that we willingly introduce into our models, but account for it explicitly. And hiding a lot of math under the carpet, what we used was adjustable robust optimization. It's an optimization-based method that deals with hard constraints, so it's very resilience-focused, but at the same time, it can be very conservative. So we studied two different formulations. The first one is static, in which case the decision maker takes a decision here and now, fixes all the decisions and anticipates the worst case outcome. whereas in the adjustable case, you have a degree of recourse upon the uncertainty is realized. I think I will skip this one because it entails a lot of math. As I said, if you want to capture with high fidelity the problem and introduce also uncertainty, you have to pay a very hefty computational premium. In this case, it's imperative that you devise some decomposition methods, and this is what we did in this work. I'm not going to go into the details. I will give the GitHub code at the very end and the paper as well. So any questions I can happily take. And what you can see here is that a single solution of the monolithic, let's say, model in the static robust case, when you just hard code this in your Pyomo or GAMS, can take up to 13 hours. But when you employ a decomposition method, you can solve the same model in half hour. So a very significant computational saving. And at the same time, when you want to introduce adaptive decision rules in your model, within 24 hours, the model cannot converge when you just solve this with state-of-the-art solvers. So you really have to think about the solution method that you proceed with. In terms of the running time of the algorithm that we developed, you can see that it scales all exponentially, like with the number of clusters, but then with the different robust formulations, it's less sensitive. So now comparing the uncertainty outlooks, this is what the spatial allocation and installation of generation and transmission looks like for both the robust and the deterministic case. What we see here is that robust solutions favor a more decentralized allocation of capacity versus an early extensive development of a transmission network within the country. And this makes sense because it's wary of the fact that the demand can actually fluctuate, so it tries to install there much more capacity compared to the deterministic solution where here greedily you try to install capacity where you have better resources. We can see that uncertainty also underpins the role of green hydrogen. We see a 30 to 50% increase in total capacity. And at the same time, we can see that the robust models tend to capture better the fact that in the industrially relevant regions, you expect to have more hydrogen installation. This is counterfactual from perspective. So what we try to do, we try to contextualize this even further. So what we do is we use the results that we have from our model. We fix our solutions. And what we do then is that we expose the capacity solutions into a Monte Carlo environment where we do different realizations of demand across the different years. And what we observe here is the fact that even though the deterministic in the short term is much cheaper compared to the robust, in the long term, where you expose this into the real world, let's say, it can lead to up to 35 to 40% increase in OPEX, which at the same time makes the robust solution 20% less expensive overall. We also conclude that static robust optimization, even though from a computational perspective being very favorable, from an economic perspective, it doesn't provide cost-competitive solutions. Last slide, this is the tool that we developed within the group. This is basically graphical user interface-based software where we have implemented all the different models and methods. So the decision maker only has to select different setups of their preference, just select those options, and then the model can run and they can perform easily their what-if scenario analysis. And this is all open source, and we don't rely on commercial solvers at all. So in conclusion, what we see from our case is the fact that cost-effective low-carbon heat requires a minimum of 25% hydrogen share. We see the effect of flexible end-use technologies that can lead to more efficient capacity utilization. We also see that when we consider uncertain, decentralized capacity allocation leads to more resilient operation. And whenever we are confronted with robust, resilient solutions, we have to also be wary about the long-term feasibility of the system. And in terms of ongoing work, we're looking to expanding the energy systems optimization model that we have to consider critical minerals for enabling transitions, as well as the European sector, and in the long term, providing accessible green computing solutions for decision makers. So with that, I will conclude. I hope I didn't run over significantly. This is the QR code where most of our codes are available and free to download, apart from the GUI. And with that, I will stop sharing my screen to see everybody again. And yeah, really hope I did. Okay, I have 2 minutes.
Thanks a lot for presentation, and you are perfect on time. It's interesting to see how to include all of these uncertainties in the modeling.